one is? Okay. So hello everyone, and thanks for inviting me. I'm Elad Hoffer, and I will present norm matters, efficient and accurate normalization schemes in deep networks. This is joint work with Ron Banner from Intel and Itai Golan and Daniel Soudry from Technion. So batch normalization has been an important building block of deep learning models over the past few years, allowing faster convergence and improved accuracy. However, it is known to exhibit several shortcomings. Amongst them are the reliance on independence between samples, making it unsuitable for several tasks, such as RL and metric learning. That it has visible yet poorly understood interactions with other organization techniques. It also incurs noticeable computation and memory impact, accounting for up to a quarter of computation time, and it requires high precision operations, making it numerically unstable. One property of batch norm which we'll use is that of norm invariance. Given an input x, a weight vector w of the preceding layer, and its direction w hat, it is easy to show that the batch norm is norm invariant. This means that the norm of the weights has no impact on intermediate activations. We derived an equation for the change in the weight's direction. The only effect of the weight's norm is scaling the rates of these updates. We believe norm invariance is the main property leading to the success of batch norm, by explicitly removing the effect of the weight's norm. First, we would like to understand the interaction of batch norm with weight decay. We showed that using weight decay on layers preceding batch norm is equivalent to learning rate scaling and can be mimicked by simply adapting the learning rate. We recorded the norm of the weights trained with weight decay and then retrained without it, modifying the learning rate to account for the change of the norm. As you can see on the graph, we were able to replicate the results obtained by weight decay with this simple learning rate modification. One appealing alternative to batch norm is weight normalization, normalizing the weights instead of activations by decoupling their norm for the direction. It is more efficient than batch norm as it requires less computations, and more suitable for many tasks as it has no assumption over the samples in a batch. Unfortunately, weight norm performs much worse than batch norm for large-scale tasks, such as ImageNet. Understanding that the norm of the weights matter, we suggest fixing the weights norm in weight normalization in a manner similar to common initialization heuristics. As you can see in the figure, we were able to improve weight norm substantially in large-scale setting, where it previously failed to compete with batch norm. In batch norm, we subtract the mean and divide by the standard deviation, which is just a scaled L2 norm of the centered inputs. If, as we suggested, norm invariance is the main property of batch norm, it is not essential to use the L2 norm. Therefore, we can choose more stable norms, such as L1 and L infinity. These norms are easier to compute, usually require less memory, and do not suffer from numerical problems of regular L2 norm. To find the correct scale factor for each norm, we required that the scaled norms would be equal in expectation. To analytically calculate this expectation, we make the common assumption that the neural inputs are approximately Gaussian. Thus, for example, to use the L1 norm, we need to scale it by a square root of pi over 2, which is approximately 1.25. We additionally checked and verified empirically that this is the optimal scale needed. Surprisingly, this small constant makes a large difference. We can see on the left that a scaled L1 normalization, marked in green, allows us to use L1 as a drop-in substitute to regular batch norm without any additional modification. On the right, we can see that this leads to the same performance as batch norm on common models of ResNet 18 and ResNet 50 over ImageNet, allowing faster computation and smaller memory footprint. Replacing L2 for L1 also allowed us to alleviate low precision difficulties of batch norm, and we were able for the first time to train ResNet 50 completely in half precision without any modifications. With a few more tricks, we were able to use these ideas in a follow-up work, also available at Neurips this year, allowing training models in 8-bit of precision. We invite you to check our work, Scalable Methods for 8-bit Training, for more details. Thank you, and see you at our poster number 27.